So we're going to continue with what we talked about last time. And if you remember, we were talking about modeling. Check me out, Runway Kopetsky. Woo! So we want to take these trig functions and we want to figure out how to model them, how to make them look their best and their nicest. What we started with was some nice, beautiful remembrance of my sine and cosine functions. We talked about the amplitude, the period, the phase shift, and the principal axis. We said all of that was super fantastical, and we like it. Then I gave you some equations like that, and I said, or functions, and I said, hey, tell me what the equation is. And so we went through the process of finding the principal axis, finding the amplitude, finding the period, and then finding the phase shift. And we got these written down nice and pretty. Okay? But now I want to work into the world of actual math problems. So I want you to read this problem with me so that I can make sure we know what's happening, so we can envision what's going on here. Suppose that we have a weight hanging from a spring, and it is set in motion by an upward push. So we got this cute little spring hanging there, and we are going to push it upwards. Get it going, right? Okay, it's going to take 12 seconds. That's a long time. To complete one cycle of moving from its equilibrium position to 10 centimeters above, and then it's going to drop 10 centimeters below. And then it's going to return to its equilibrium position. So here's what we got. We got a weight. We're pushing it upward. It's going to go all the way up 10 centimeters above where it started. Then it's going to go down to 10 centimeters below where it started. And then it's going to go back to its regular spot. Can you envision what that's going to look like? In your brain, can you see what's going on there? Yeah, just in general. Can you imagine having a spring and me putting something on it and pushing it up and then it's going and bouncing and bouncing and bouncing and bouncing? Joseph says he can envision it. I don't know if anybody else can, but we'll go with one. All right, so I've got this spring, so I'm going to draw my cute little spring. Right, and at the bottom of that spring, see my weight right here? It's really heavy. So here's my weight, right, and it's like, oh man, it's really heavy. So there's my weight. My job is to start by pushing it up, and it's going to go up, and then down, and then down, and then up. Cool? Okay. So what I need to interpret from this problem right here, it tells me we want to sketch a graph of this function. Okay? If I want to sketch a graph, I need to know a few things. I need to do some interpreting. So I'm going to come up here into this math problem, and I am going to figure out what on earth is going on. First thing I need to know is how long I need my graph to be. Well, this says it's going to take 12 seconds to complete one cycle. Well, that's a good thing. That means I know I need to deal with this 12 somehow, right? Then it says that the other thing that we know is my graph goes 10 centimeters above, and then it goes 10 centimeters below. Okay, so here's what I've got. Here's what I'm going to do here. I am going to use that information right there, and I'm going to say, hey, check me out. I know for a fact my graph is going to utilize 12 centimeters. So I'm going to say this right here is my time, and my time is being measured in seconds. And I am going to use my distance, and I'm going to say that my distance is measured in centimeters. So these are the first two things I need to figure out. According to the word problem, my entire cycle is 12 seconds. So I have a 12 second full cycle. That's pretty awesome. So that means on my x-axis, I need to go all the way to 12. Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Beautiful. There's my 12. And we're in the world of seconds. And so I'm just going to put some significant marks here. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So there's my 3, 6, 9, and 12 seconds, right? It's nice if I split things into fours. Okay? Now, the other thing we talked about is the distance. We said that in this world of that 12 is my full cycle. I also told you that it has 10 centimeters up and 10 centimeters down. So that means on my graph, in my distance world, I need to make sure I get up to 10. So I don't have 10 spaces, 1, 2, 3, 4, 5, but I can count by twos, and I can say that this is 2, right? It's 2, 4, 6, 8, so I can put the little 6 right there just as a reference. And then if I'm going below 2, 4, 6, 8, 10, there's negative 10. There's my negative 6. So now I've got my distance going to the up and to the down. Now when I look at how this spring all started, it says that my spring started at 0, started here, and it took 12 seconds to go the full cycle. So in that 12 seconds, it ended up right back here. So there's my 2 points that I know. I know I was at 0 at the beginning, and then I know I was at 12 at the end. According to the words, I gave this guy an upward push. So that means from here, it went to the up. Hey, we like that. So it's going to the up. Now I got to figure out how it did this. That cycle went to the up, all the way up to 10 seconds, and then it went down back to equilibrium, and then it went down below 10 seconds, and then it went back up to 12. So that means halfway between the beginning and the end, it crossed that equilibrium point again. Since I went up first, halfway between the beginning and that first equilibrium point, it made it all the way up here to that 10 seconds. Halfway between when it got to that equilibrium point and the end, it made it all the way down to 10 seconds, or 10 centimeters. I keep saying seconds, I'm sorry. So now if I look, starting here, giving it a push to the up, this actually goes to the up, to the down, to the down, to the up. And it's going to continue that pattern every 12 seconds. So it's going to go to the up, to the down, to the down, to the up, to the up, to the down, to the down, to the up. So when I look at this graph, now that I have it drawn, what type of graph does this look like automatically? Does it look like a sine graph or a cosine graph? It looks like a sine graph. So because I'm going to the up, to the down, to the down, to the up, remember, to the up, to the down, to the down, to the up, this is sine. Nice. I like it. So when I say, hey, draw a graph, this is what my graph looks like. That's my graph. No, it'll continue. That's what that arrow means, right? If I have no friction, I have no air pressure, air resistance, all that stuff, it's going to continue that forever. But in real life, we're not living in a vacuum, so it doesn't quite do that. Now, first thing, sketch the graph. We did that. Now it says write a cosine function to represent the position of the weight. Dang, Ms. Kopetsky, that's not nice. I don't want to write a cosine function. I'm going to click here and say, oh, hey, write a sine function. That's the one we want. So we're actually going to do part C first, and then we're going to go back and do part B. Okay? Because when I looked at my graph, it looked like a sine function. I'm going to start with that one. Okay? So here, sine function. Let's do this. Here we go. In order to write a sine function, I need a few things. I need an A, a B, a C, and a D. I need A, which is the amplitude, B, which controls the period, C, which controls the phase shift, and D, which is the principal axis. A is amplitude. Do I know how tall this graph is from the principal axis? Oh, dang, I got to start with my principal axis. So that's D. Where is the middle of the graph from the top to the bottom? It's at 0. So my D is 0 because my principal axis goes right here. Let me get my highlighter. My principal axis is right here on the x-axis, which means that principal axis has an equation of y equals 0, which tells me that my D is 0. Now from that, how high up do I go to the highest point? 10. So that tells me my amplitude is 10. Dang. All right, now, B I find from the period of the function. Remember, when I have a graph, I can see the period, but I cannot find out what B is until I do a little bit of mathiness. Okay? Remember, my formula is the period equals 2 pi over B. I don't know B, but I do know the period. How long does it take me to complete an entire cycle of this graph? Well, it takes me 12 seconds. Since this takes me 12 seconds, I know 12 is equal to 2 pi over B. Oops. Now that 12 is equal to 2 pi over B, I get to go ahead and solve that. Remember, solving it means I switch these guys, and I find out that B is equal to 2 pi over 12. And 2 pi over 12 gets reduced so that my B value is pi over 6. Score. Now I need my C. My C is my phase shift. So for phase shift, I need to know how much did this graph get moved to the left or to the right. Well, sine is supposed to start at the origin or at the principal axis and go up, down, down, up. Hey, that's what it does. So I have no phase shift. There is none. So that means my C is also a 0. So my A is 10, my B is pi over 6, my C is 0, and my D is 0. So if I'm going to write a sine function, what that means is down here in my world of sine functioning, I get to say, hey, watch this. The distance with respect to the time is equal to 10 sine, parentheses, pi over 6t plus 0 plus 0. This right here is my sine function. In order to get my cosine function, I have to look and see what has happened and what has changed. For cosine, I want my graph to start at the top and go. Whoops. Whoa, 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 whoa. I want my graph to go, whoa, 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 whoa. What is it doing? Okay. I want it to go to the down, to the down, to the up, to the up. That's what I want for cosine. So that means I need to look for the maximum spot to find out how much it got shifted over. So now when I do this, I look at my maximum location right here, and I say, hey, check me out. My maximum spot is right here, which has actually been moved over 3 spaces. So now for cosine, I'm actually going to do some thinking and some talking and some writing. Because for cosine, my phase shift is 3. Now my formula for C is the phase shift, I'm going to come right here in this space, the phase shift is equal to negative C over B. I know that my phase shift is 3. I don't know the C value, but I do know the B value. So here, to work this problem, I'm going to say that 3 is equal to negative C over pi over 6. Well, to solve that, I need to multiply both sides by my denominator, and my denominator is pi over 6. So now I get pi over 6 times 3 equals negative C. Well, I don't like that negativity right there, so I know I've got to multiply by a negative in the long run. So this is going to tell me that my C value is equal to, these cancel out, that's a 1, that's a 2. So this becomes pi over 2. Because I got rid of that negative, that means I moved it over there. I multiplied or divided by a negative 1 as well. So my C value now is negative pi over 2. So for cosine, everything else stays the same. So I go back to my graph right here, and I say, hey, my cosine function, I'm going to say d of t equals, amplitude is the same. Oops. My function has changed. My period is the same. This time I have a phase shift. I just said my phase shift gives me a C value of negative pi over 2. And my amplitude is still 0, so I don't have to change that. Hey, that's kind of nifty. Kind of fun. I like this. Let's look at a second guy. What if we're talking about a Ferris wheel? Do you know what a Ferris wheel is? It's a wheel. That's Ferris. Duh. Right? Do you guys know what a Ferris wheel is for real? For real?
Oh, like the ones that go like that, right?
Yeah. Wow.
It doesn't feel wrong Ferris wheel?
All right. A Ferris wheel looks like this. It's that circle thing.
Have you ever ridden the Ferris wheel in the left of sea, right?
Yeah.
I got it once. It was so high. and then it stopped. We were like at the very top.
Uh-huh.
And then the people I was with kept rocking it. It was scary.
All right, and so if we're at the state fair right here, and it's got all the spokes that come out like this, right? And then at the state fair, I hate these things. It says Texas Star. So right here it says Texas. And then Star. Right? Yeah? Okay. So here we go. As you ride the Ferris wheel, your distance from the ground varies periodically with time. Well, that's true, because as I ride this thing, right here, where am I? I climb on right here, and then we follow around the Ferris wheel, right? So we go up, 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 up. We get to the tip, tip, top, and then we go down, 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 down. right? Let t be the number of seconds that have elapsed since the Ferris wheel started. At the highest point, you are 43 feet above the ground. The wheel makes a revolution once every 8 seconds. So this is like a really fast Ferris wheel. We're like gonna fly off. And the diameter of the wheel is 40 feet. I don't know why I don't change that. It makes me laugh every time I pull up this problem. Can you imagine being on the Ferris wheel at the state fair and you start right here and 8 seconds later you're all the way back down? I think that should be 8 minutes, but whatever.
Wait, 8 seconds?
Should we change it to minutes?
I don't think 8 seconds is
Or do we want to leave it as seconds?
Yeah, let's do that second.
Let's leave it as seconds. Okay, we'll leave it as seconds. We know this is ridiculous and we'd all fly off, but it's okay.
No,
Alright.
because we're in a cage.
See, I couldn't find a Ferris wheel, so I did the log ride instead. Sorry, guys. Lame. Alright, so here we go. Can we sketch the graph of what's going on? Well, we need some serious figuring out going on here. I have a Ferris wheel. What do we know for sure about this Ferris wheel before I start sketching the graph? The highest point is 43. So I know over here, this tip top is at 43. Okay? What else do I know? The revolution's 8. I like that. Okay? We don't care if it's really seconds or minutes. We're just going with 8, and I'm going to laugh at it. Okay, what else do I know? The diameter. How does that help me out? Why on earth would I tell you the diameter of this thing? It's like 30? Oh, 3. I thought you said 30. I was like, what? Okay, so if from here all the way to here, which is the bottom, right, is 40, that means this is at a level of 3. Does that make any sense whatsoever? Does it make sense that the lowest point of the Ferris wheel is at 3? 3 feet.
Yeah.
Why? Yeah, can we have the Ferris wheel scraping the ground?
No.
No, because then everybody would die in that 8 seconds when it goes whoosh, then you would just crash into the ground, right? So this Ferris wheel has legs. These legs keep it off the ground so that we actually don't kill ourselves when we're riding this 8-second Ferris wheel, right? So we might kill ourselves by getting thrown off with the projectiles, but we are not going to kill ourselves with hitting the ground. So this right here, this 3 and this 43 and this 40, this actually will be interpreted on my graph. So we know it's 8 seconds, we know the diameter of the wheel, we know the height maximum, we know the minimum. All right? So I'm going to go to my trusty graph paper. My trusty graph paper. So let's see what's going on here. So this time, here's what we know. Ooh, this is not very nice. So now we know that my top of the Ferris wheel is at 43. We know the bottom is at 3. Cool? We know that the time takes 8 seconds to complete. Ooh, we can't even see that. So this is 8 seconds. Why does this pen not show up? Okay, there we go. So it takes 8 seconds to go the full cycle. So now, here's what I'm going to do. I'm going to set it up. I'm going to say, hey, watch this. This is 0. I got to come over here and I got to find 8. 1, 2, 3, 4, 5, 6, 7, 8. Eee. Okay, we can do that. So here's my 8. Okay. Now, this is the part that's going to be crazy and chaotic. I've got to get all the way up to 43. If I want to count here, I'm actually going to count by 5s. Nope, that ain't going to work. But we'll make it work. Right, so I need to move my axis down. So watch me. Watch what I'm going to do. I'm going to take my cute little whiteout. I didn't use my erasable pins. I know, that's lame. I'm going to move my x-axis down so that I have room. So let's get rid of that 8. Huh? I know, I'm flexing with my whiteout. You, too, can use whiteout. So I'm going to come down here. I'm going to put it down this way because we're not going underground. So here we go. Oops. Look, I can't even use a straight line drawer. I made a crooked line. How is that? Hey, Miss Petsky, you drew a crooked line when you were using a straight line drawer. Okay, so here we go. Ah! Okay. I'm going to come over here. 1, 2, 3, 4, 5, 6, 7, 8. Now I got to go up 9 spaces because I'm going to count by 5s. 5, 10, 15, 20, 25, 30, 35, 40, 45. 5, 10, 15, 20, 25. So I'll go with 25 right there. Okay. So I know. This is my little window right here. So now tell me, where do I start on this graph? I'm starting below 5 and at 0 because I know I start at the bottom. This is a Ferris wheel, right? So I have to start at 3. So right here, I'm going to put my dot at 3. Cool? At 8 seconds, where am I? I'm at the end. So I'm right back here where I can get off. Agreed? When do I get to the tip top? No, I am at 43 at the tip top. When do I get there? At 4 seconds. So I know at my halfway mark, here we go, 4 seconds, I am up to the tip top, which is at 43, which is like right here. Okay? I'm actually going to put my ordered pairs so that I know this is at 4:43, this is at 0:3, and this is at 8:3. Okay? Now talk to me here because this is where things get fun. Okay? We know this one is the height, so I'm going to put 8 of t. And I know this one is my time, so I'm just going to put t here. And this t is my seconds. And I think my height was in feet. I don't remember. We'll look again. Okay? All right. Question. Where's halfway? How high up do I go when I'm going halfway? So if I start at 3 and I go up to 43, where is halfway? So when I'm going along here, I start here, that's at 3. I go around, that's the top. This about is my halfway spot, agreed? Where? That's where that center of the Ferris wheel is. Where is that halfway spot? How high up is it? How can I figure this out? Well, let's think of the world of circles. I told you one handy piece of information about this circle. What did I tell you? The diameter. What do we use for halfway? Half the diameter, which is called the radius. How much is my radius if the diameter is 40? The diameter is 40, the radius is 20, right? So if I'm starting at 3 feet, where will I be at the halfway point? At 23. So here's what's going on. I know that my diameter is 40, which tells me my radius, so if the diameter is 40, the radius is 20. Well, that's kind of nifty. So if I'm starting at 3 and my radius is 20, I need to go up 20 spaces from there. 20 spaces added to that 3 gets me 23. So I can say the principal axis of this guy is going to be 23. So that's going to be right here. And I'm going to draw my there. Now another fun thing that we want to figure out is if it takes me 4 seconds to get to the tip top, how many seconds does it take me to get to my halfway spot? If it takes 4 seconds to get all the way to the top, how many does it take me to get to my halfway spot? 2. What about how many to get back down to my halfway spot? That's going to be at 6. So now I'm going to draw my cute little graph. There we go. So now I'm going to go whoop, because here and here, and then guess what happens again? Once I get to the bottom, they're really nice and they're like, oh man, you paid $47 to ride this? So guess what we're going to do? We're going to go again. So now we're going to go whoop, whoop. So is it a quadratic? Not anymore. It never was actually, but it looked like one. So what kind of graph is this? It's like a sine or a cosine. Oh my gosh, this is amazing. So let's look. How can you guys not enjoy this as much as me? So we sketched a graph. Now let's look. Let's write an equation. You pick. Do you want a sine or a cosine? Cosine. All right. Joseph said cosine. So that means we're going to write a cosine equation. Now remember, cosine, we typically say we go to the down, to the down, oops, to the up, to the up. Does this one do that? No. What does this graph do? So it goes to the up, to the up, to the down, to the down. So what do you notice? If our graph goes to the up, to the up, to the down, to the down, is that cosine? Is it sine? No. So what do you notice though? It's the opposite. Holy cannoli, what can we use if it's the opposite? What can I do to flip my graph from going down, down, up, up? I can use a negative. So since it's exact opposite, I can write a negative cosine function. Oh my goodness, this is the greatest. What? Okay, so now we still need to figure out my things. I need my A, my B, my C, and my D. D is the principal axis. Do we know where the principal axis is on this graph? It's at 23. So here we go. H of T equals. H of T equals. I know it's going to be negative. That's right there. I know at the end I've got a plus 23. Cool. I know it's going to be cosine. All right, D is 23. Do I know my amplitude? How long does it take me to get from 23 up to the top? How long, remember amplitude, amplitude is from the principal axis up to the top. This right here is my amplitude. Now, when I ask you for your amplitude, we're talking about the vertical distance, not the time distance. How many units is it from the principal axis to the top? 20. So in this case, my amplitude is 20 spaces. Remember, that is 43 minus 23. Okay. So that means my A value right here is 23. And since we flipped it over, I'm actually going to put a negative with that 23. Oh, look at me being snazzy. All right, now B represents the period of the function. That means we need to know how long it takes to go the whole thing. The whole shebang, according to this right here, is 8 seconds. Oh, it's 20. You're right. Sorry. It's 20, not 23. Thank you, Joseph. 23 was the D. Okay, so now, this says my period is 8 seconds. My period is always 2 pi over B. I know that this is 8 equals 2 pi over B. To find the value of B, I switch these two bad boys right there, boop, 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 and I say that B is equal to 2 pi over 8. Can I reduce? Sure I can. 2 pi over 8 gives me pi over 4. Now, since we know we're using a negative cosine, instead of starting at the tip top, I have to start at the way down low. Am I at the way down low when I look at my graph starting? Yes. Since I'm starting at the way down low, I don't have to have a phase shift. So there is no C value on this one. So here we go. I'm going to fill in my cute little graph right here. This is going to be a negative 20. My B is pi over 4 times T. Close my parentheses, and I move up to a plus 23 for my amplitude. All right, so I'm going to stop right there.